Okay, welcome back everybody for today's session of the Cardiff analysis seminar. So we are delighted to have Matthew Colbrook from Cambridge, who will talk about Koopman operators and the computation of spectral properties in infinite dimensions. So thank you very much for accepting our invitation, and over to you.
Great. Well, thank you for the invitation as well. It's a pleasure to be here and meet some familiar faces and also make some new friends. So I'm going to be talking about Koopman operators. So don't worry if you don't know what those are at this stage. That will hopefully become clearer as we go on. This work is based on a joint paper with Alex Townsend at Cornell. And the paper is called Rigorous Data-Driven Computation of Spectral Properties of Koopman Operators for Dynamical Systems, and you can find it on the archive. I'll also put this work into a wider framework of a foundations program on the computation of spectral properties, which I'm sure many of you are familiar with. Some of you probably aren't, but I'll explain how that sits as well. Just to whet your appetite, these are fully nonlinear eigenmodes of this Koopman operator, computed in ambient dimension 300,000. Okay, so you've got an infinite dimensional operator acting on a physical space of dimension 300,000, corresponding in this picture to turbulent flow with a Reynolds number of 10 to the 5. And we're able to do this with explicit error control. So we'll see how to do that at the end of the talk. Okay, so the setup for the talk is the following. I have some discrete time dynamical system with a state x and some state space omega. And the dynamics are governed by a function f from omega to omega. So the state at time n+1 is given by f of the state at time n. And all I'm given access to when I'm studying this problem or this system are snapshots of the following form: a collection of x's and y's where y is equal to f of x. You could consider the noisy case as well, where it's approximately equal to f of x, but just for simplicity, let's assume we have noiseless data. And then the broad goal is to use this snapshot data. So it's called snapshot data because you imagine taking snapshots of the dynamical system in time. The broad goal is to take the snapshot data and learn properties of the dynamical system. Okay, I'm going to be a bit sort of vague about what I mean by that. But some applications of this problem arise in a whole host of different areas. Here's a very incomplete list. We'll look at fluid dynamics and molecular dynamics towards the end of the talk. But essentially, whenever you have anything evolving in time, even if it's a continuous time dynamical system, you could imagine taking discrete time snapshots, it can be put into this broad framework. Okay, so some immediate challenges with this broad goal. F is unknown, so I don't assume I know F. F is typically nonlinear. And the system could also be chaotic. So that means if you start off with two points that are close together, they can quickly diverge as time proceeds. Okay, so the way I'm going to study this problem, it goes back to a beautiful idea of Koopman in the 30s and also von Neumann. So they wrote a paper together, although the original one was by Koopman, where they looked at, rather than the state x in omega, they looked at functions of the states on the state space. So you have an observable g or a function g on the state space to the complex plane. And then you define something called the Koopman operator, which is just this composition operator with f, which governs the dynamics. Okay, so k of g, well, this is a function. How do you evaluate it? It's at the point x. Well, you take g of f of x. And you can convince yourself that this is a linear operator. You need to be a bit careful about its domain. So what people typically do is they study it in an L2 space. You might take a small omega, a measure on large omega, the state space, and then look at observables which are square integrable with respect to that measure. Oh, was that a question or? Okay, I'll just continue. So this operator K is linear, but because it acts on a function space, the price you've paid for this linearization is that it's infinite dimensional. Okay, so let me just go back a slide. So we started with this nonlinear dynamical system in finite dimensions. we've sort of done this linearization. Remember, we still don't know F. Okay, so K is unknown at the moment, but we've linearized the system and we've gone to an infinite dimensional operator. And what you want to do is you want to learn the spectral properties of K, of this operator, via the snapshot data, because in turn, the spectral properties of K will encode all of the information about the dynamical system. Okay, so the spectrum of this operator is just Z, such that K minus Z is not invertible. We're going to look at ways to compute this. We're also going to look at ways to compute spectral measures associated with Koopman operators as well. Okay, so before I explain why spectra are important, I just wanted to show you this sort of Google Scholar search. So parallel to the current interest in deep learning, there's been a bit of a revolution or renaissance in dynamics in the big data era. And this goes back to this paper here in 2004, which studies something called the Koopman mode decomposition, which I'll define in the next slide. But you can think of it as a spectral decomposition of the Koopman operator. And so if you search for papers on Koopman operators since 2004, when this paper came out, you'll get about 80,000 results. And the majority of these papers consider specific applications of this framework to a given dynamical system. So there's very little on actually how you rigorously compute spectral properties of the Koopman operator, and that in some sense is the gap that we're trying to fill with these results. Okay, so why spectra? Well, I've already given you sort of a vague answer in that somehow it encodes the information of the system. So for example, if you have an eigenvalue eigenfunction pair, so lambda and phi lambda of K, and suppose you want to evaluate this eigenfunction at a future time, okay, at time n, then this is the same as evaluating at f applied n times to the original state x naught, which is the same as the n-fold application of the Koopman operator. And then because you assumed this was an eigenfunction, you just draw out the power of the eigenvalue. So that's sort of the easy case. More generally, if your system is measure preserving, okay, so it preserves volume, then any G in your Hilbert space will have an expansion in terms of a sum. It could be an infinite sum of eigenfunctions. So this is the discrete part, sorry. And then this continuous spectral part as well. So you can think of these phi thetas as a continuously parameterized set of generalized eigenfunctions. So you get the spectral decomposition of any function or observable G. And this gives you something called the Koopman mode decomposition, which is just how this observable behaves as you iterate f, as you iterate time. Okay, so you get the same.
Can I ask a question, Matt?
Yeah, sure.
Is it obvious that K is self-adjoint, say, or unitary?
Oh, no. Yes. This will be something we touch on in the second part of the talk. Yes, okay. That's a great question. So if it's measure preserving, K is actually an isometry. So to get this kind of representation, you need to consider unitary extensions, and then this will be a measure on the unit circle, and then I'm just looking at the parameterization in terms of the angle. So you can think of, in this case, the easiest case is that K is a unitary operator. For example, if the system is Hamiltonian.
Okay, thanks.
Okay, so given such a representation, we get the Koopman mode decomposition where we apply K n times. Okay, we already know how an eigenfunction behaves due to this formula here. And then we get this sort of Fourier transform or Fourier series behavior over the continuous spectrum. And this is what people commonly call the Koopman mode decomposition. So if you open up one of those 80,000 papers on Koopman operators, within the first paragraph or so, they'll start talking about the Koopman mode decomposition, albeit probably with some lack of rigor. So typically people only write down it for a finite sum of eigenfunctions. But you do need to consider this continuous spectral component as well. Okay, so a global understanding of nonlinear dynamics in state space has been called a mathematical grand challenge of the 21st century. So this was in a recent paper of Brunton and Kurtz, who are two of the big players in Koopman operators, or Koopmania. Let me just explain why they're calling this problem a grand challenge. Well, if you go back to sort of the classical way of viewing dynamical systems, a lot of it is geometric, right? So you look locally around a fixed point or a stable manifold or something, and then you try and figure out how does the system behave in a local manner. You can think of the Koopman operator as sort of a global linearization. Okay, so you're somehow getting a global understanding of the nonlinear dynamics. So that makes it typically very hard, and that's because we've gone up to infinite dimensions. So there are four big well-known challenges in this area. The first is dealing with continuous spectra. So whenever you discretize your operator, say to a finite truncation or projection, you're always going to lose continuous spectra. So you need to be careful how you do that. You might not have a non-trivial finite dimensional invariant subspace. So let me just go back here. So if we ignore continuous spectra for a second and just look at this expansion, if this expansion isn't finite and we approximate G by a finite number of eigenfunctions, then as we iterate K or move forward in time, we're going to escape that invariant subspace. Okay, so that can be a challenge. Another problem is spectral pollution. So if you take a truncation of your operator to a finite dimensional onto a finite dimensional subspace, typically when you then compute the eigenvalues, you get false eigenvalues due to the truncation. So these are known as spurious modes or spectral pollution. And another challenge is how to deal with chaotic behavior. Okay, because remember, we're trying to do all of this by just observing snapshots of the data from trajectories.
So these can only be autonomous dynamical systems, right?
Sorry?
The dynamical systems you were talking about have to be autonomous.
Oh, yes, yeah. That's another very good question. You can, if you consider a more complicated object, there are ways of extending this framework to non-autonomous, but it becomes very, very difficult. We can chat about that at the end if you're interested. Okay, so the ways I'm going to try and tackle these problems in this talk are to compute smooth approximations of spectral measures with explicit high-order convergence. I'm going to try and compute the spectral properties of K directly rather than compute a finite dimensional invariant subspace. I'm going to compute residuals associated with the spectrum with error control, and this will allow me to provide an algorithm that converges to the spectrum and also avoids spectral pollution. And all of the algorithms that I'm going to talk about can handle chaotic systems if you just use single time steps. So let me just go back to this picture here. You could, for example, imagine collecting data along a single trajectory, okay? Or you could imagine lots of initial conditions and then going forward one time step. So you can apply these algorithms in either context, but in chaotic systems, it's more appropriate to do the latter. Okay, so that's the broad goal of this talk, is to show you how to solve these problems. The first part is going to look at computing residuals and spectra. And in this part of the talk, we're going to consider general Koopman operators. So I'm not making any assumption on my underlying dynamical system. The only assumption is that K is a closed operator on this L2 space with a domain, and I'm going to denote the inner product of this space via these angled brackets. Okay, so we're going to start off by looking at something called extended dynamic mode decomposition. Now, this goes back to a paper of Williams and co-authors in 2015. And the idea is essentially just a Galerkin approximation. So you might have heard of something called dynamic mode decomposition, which is sort of the, I guess, the algorithm that's used the most in Koopman. And this dynamic mode decomposition is a special case of extended dynamic mode decomposition. Okay, so you start off with a subspace of your L2 space, spanned by some dictionary functions, psi j up to nk. Okay, so I'm going to assume that this space has dimension nk. For notational convenience, I'm going to collect the dictionary into this quasi-matrix Okay, so if I evaluate at the point X, it gives me back this row vector. Now for my data, remember I have X and Y equal to f of X. I'm going to define two matrices corresponding to the dictionary evaluated at the points X, just stacked row-wise like this, and similarly for the Y points. Okay, so that's all just notational convenience. So given G, a function in this finite dimensional subspace, we can expand G in terms of the basis functions. And then we can seek a finite matrix, KEDMD, which approximates the Koopman operator by acting on the coefficients in this expansion. Okay, so K of G is approximately equal to this sum of these functions, where these are the new coefficients. So a very natural thing to do is to look at minimizing the squared error of this approximation. Okay, so we might integrate this squared error over the measure on omega, and then seek a matrix KEDMD that minimizes this this integral. Now, of course, we're not assuming we know K. Okay, so we can't access this this integral directly, but we can treat the X points as quadrature points with specific weights. So, for example, you could imagine X could be collected at random, and then you've got some sort of Monte Carlo sampling. Or if you have an ergodic system, you can collect them along a single trajectory and then use a quadrature rule corresponding to the Birkhoff's ergodic theorem. Or you could, if you had access to the measure, explicitly compute high order quadrature rules if the dimension D of your dynamical system was not too large. But anyway, regardless of how you view that, or the sort of the scenario you're in, what you do is you approximate this integral via this quadrature rule, and it reduces the problem to a standard weighted least squares problem. Okay, where I've just evaluated the integrand at the point X and written it in terms of these two matrices, psi X and psi Y. Okay, so you can write down an explicit solution of this problem given here, where capital W is this diagonal matrix of the quadrature weights. And this is a very nice form. Okay, you've got psi X star, so the star is the adjoint, W psi X, dagger is the pseudo inverse, and then you've got psi X star W psi Y. Now, the correct interpretation of this is that as you collect more and more data, assuming your quadrature rule converges, what in effect you're doing is a Galerkin approximation of the Koopman operator, because this matrix here will converge to the Gram matrix of the dictionary. So that's telling you the orthogonality properties of the different functions. And this part of the KEDMD matrix will converge to this inner product here, corresponding to the action of K on the basis functions. Okay, so what people typically do.
So what if I'm very unlucky and I chose my psi's are exactly are fixed by the flow, for instance?
Psi's are fixed by the flow.
Yeah.
Do you mean the data points are fixed by the flow?
What do I mean? Yeah.
So you're asking what happens if the data points are sort of unluckily? Yeah. That's a great question. So you do have to make an assumption here that in the large data limit, these data points are coming from some underlying quadrature rule. So for the flow problem, if you have an ergodic system and you collect along a single trajectory, then what you're effectively doing there is you're approximating the dynamics on just the ergodic component. So there, actually, that component is usually the object of interest. But you could consider, for example, different regimes within the dynamical system. For example, there might be a transient regime or a regime where you're close to that limit, and then you have to do things a bit differently. So do things either randomly or with a high order quadrature rule. So yes, you do have to have some type of result that will say that this This is approximating some quadrature rule. And then another question is, what should this measure, small omega, be? And again, that can be very difficult to answer in practice. For Hamiltonian systems, omega is given to you. Okay, so it would be natural to consider the usual Lebesgue measure. For others, you're not so lucky. So yes, the Koopman operator does depend on this this measure, and then therefore implicitly on the
I'm just trying to wonder what information do I need to have up a priori? What do I need to know?
So okay, so
set out. What do I need to know?
So if we try to make it as general as possible, if this smaller omega was a probability measure, you'd only need to know that probability measure, and then you could pick the initial conditions randomly and under some suitable regularity assumptions on K, which you can derive in terms of the function F that governs the system. So this capital F here, you could get convergence with a Monte Carlo rate. So that's probably the most general setting. Does that answer your question?
Yeah, I'll think about it. Yeah.
Yeah. Okay, so you've got this Galerkin approximation in the large data limit, and what people do is typically take the eigenvalues and eigenvectors of this approximation and compute and use them to approximate the spectral properties of the Koopman operator. So we'll see why that goes wrong in a second. So suppose you've done that and you've got a candidate eigenfunction eigenvalue pair. Okay, so G is a candidate eigenfunction, lambda is a candidate eigenvalue. To measure the accuracy or the error, you might want to compute this squared residual. So this is one way of doing it. And if you sort of expand the squared residual, you can do so in these 4 inner products, and then you can approximate these inner products using the same quadrature rule as before. And what you end up with is this matrix product involving this nonlinear pencil in lambda. Now, let me just go back one slide. Remember, we had psi x w psi x and psi x w psi y. Here we have psi x w psi y, or rather the adjoint, and then the same matrix here, and then psi x w psi x. We've now got an additional matrix, psi y w psi y, which corresponds to, at least formally, a Galerkin approximation of k star k. So it's a very simple trick. This you can construct the approximation of this matrix using the same data, and for free you've got this approximation of the residual. And once you've got this approximation of the residual, you're in business. You can start to do all sorts of things to compute the spectral properties of K. So a very sort of naive first attempt is to just clear up spectral pollution. Okay, so we have this approximation of the squared residual in terms of that pencil that I had on the previous slide, and then an approximation of the norm squared of G. So the algorithm is you first get this matrix, KEDMD, you compute its eigenvalues and eigenvectors. And then for each pair, you compute the residual, and you discard any eigenpairs where this residual is too large for a user-defined tolerance epsilon. And if you do this, then you can show that in the large data limit, you avoid spectral pollution. Okay, so the maximum of the reciprocal of the resolvent norm on the output of this algorithm is bounded by epsilon in the large data limits. But typically, you don't capture all of the spectrum. Okay, and this is because the eigenvalues of this Galerkin approximation, even as nk, the number of basis functions, increases, doesn't necessarily approximate all of the spectrum. Okay, so to overcome that, we compute something called pseudospectra. Okay, so pseudospectra, for those of you not familiar, you give it an epsilon, and then this is the definition of the pseudospectrum. They're just unions of spectra of perturbed operators. Okay, so you take the union of spectra of K plus B, where B is all operators of norm bounded by epsilon. I'm assuming implicitly here that K is bounded. There's a similar type of formula for the unbounded case, but it's a bit more technical. But the key point is that as epsilon goes to 0, this pseudospectrum, or this sort of fattened up version of the spectrum, will converge to the spectrum, and in fact monotonically. Okay, so you can compute pseudospectra using these three matrices. So we've called the algorithm ResDMD for residual dynamic mode decomposition. So the algorithm is very simple. Over a computational grid, you compute the minimum of the residual over G in your finite dimensional subspace. This is just a generalized singular value problem. And you then output those Zs that have the minimum residual below epsilon. Okay, and you can also compute the right singular vectors of this generalized SVD problem, and these will give you so-called epsilon pseudo eigenfunctions. Okay, so what you can do with this is you can prove that you don't get spectral pollution. So your output is guaranteed in the large data limits to live inside the pseudospectrum. And then this will converge uniformly to the pseudospectrum as the number of basis functions increases, assuming that you're getting a density property of the dictionary. Okay, so you can also play around with this type of algorithm to develop ways of decreasing epsilon to compute the spectrum and things like that. It's a bit more complicated to write down, but in principle, it's relatively straightforward. Okay, so let's look at an example of this before we move on to spectral measures. So here I've taken the nonlinear pendulum. So there's an angle coordinate x1 and a momenta x2. My state space is this periodic domain corresponding to the angle times r corresponding to the momenta. So the functions, the basis functions, are going to be Fourier tensor product with Hermite functions to capture the momentum. And on the right, I'm going to show you the computed pseudospectrum of the algorithm as this gray cloud. The true spectrum of this operator is this circle, okay, just the unit circle, this red circle. And the magenta dots will be the eigenvalues of the K-EDMD matrix. And I'm going to show you this as I increase the dimension nk of my subspace that I'm looking at the Koopman operator on. Okay, so let's see what happens. What you see is that the pseudospectrum will converge to the correct pseudospectrum, which is just this tube around the unit circle. But if you just look at the eigenvalues of these finite truncations, you get severe spectral pollution. Okay, so that's all these sort of false eigenvalues in the middle corresponding to the truncation rather than the actual operator itself. And this operator is also very difficult because it doesn't have discrete spectrum. The spectrum is continuous. Yes, so that's a rather distinct problem to spectral pollution, but you can see clearly that having this sort of way of approximating the spectrum or pseudospectrum gives you a way of telling which of these eigenvalues are in some sense accurate and which ones are not. Okay, so these are the pseudo eigenfunctions for that particular example. Lambda is the point in the spectrum, okay, and then you've got a frequency component, and you see that as we go around the circle, we get more and more oscillations. The color represents the complex arguments. So remember, these are functions. So on the angle x1 and momentum x2, and it might be hard to see, but there's sort of shadowed steps in these figures as well, which show the modulus of the function. And all the residuals for these pseudo eigenfunctions were smaller than 0.05. Again, I should stress that this example has empty point spectrum. Okay, so these aren't sort of approximating proper eigenfunctions, but they're giving you sort of these pseudo modes. Okay, so that's spectra. We're now going to look at dealing with continuous spectra and computing spectral measures. So going back to the question I received earlier, here I am going to assume that my dynamics are measure preserving. And this is equivalent to K being an isometry. Okay, so it preserves the size of G, the norm of G, where G is any L2 function. And for those of you who care about such things, to actually define a spectral measure, I have to consider unitary extensions of K. And you can do this in a canonical fashion. And I'm not going to sort of comment on that any further, except if someone asks about it. But you should think of this as computing spectral measures, which I'll define in a second, for an operator whose spectrum lives inside the unit disk. Okay, so it's an isometry. So a quick recap of what the spectral measure is, for those of you who haven't seen it. If we have a finite dimensional matrix A that commutes with its adjoint, and then it has an orthonormal basis of eigenvectors, Vj. So you can write out any V in your finite dimensional space as a sum of these spectral projections acting on V. So these are projections onto the eigenspaces. And then AV is given by this, this formula here. So you get diagonalization. When you jump to infinite dimensions, for an operator L with some domain on a Hilbert space H, typically there's no longer a basis of eigenvectors. So you have to consider something called the spectral theorem, which gives you a projection valued spectral measure, E. Okay. So E you can think of as a measure in the usual sense, but rather than spitting out a scalar, it spits out a projection. So you give it a set U, it'll spit out a projection EU corresponding to the spectral content of the operator on that set U. Okay, I'm going to convince you that this is just a Fourier transform in a second. But any G in your Hilbert space can be written as this integral over the spectrum with respect to this projection valued spectral measure. So you just replace this sum by an integral, and then LG acts in exactly the same manner in finite dimensions, except you're now integrating lambda against the spectral measure. What people typically do is look at scalar valued versions of this, where you take inner products with a function G or a vector G rather. Okay, so you consider the scalar valued spectral measure, which given a set U will compute this projection EU, act on G, and then you take an inner product with G. Okay, so this is just a Fourier transform. For example, if you take the minus Laplacian and consider it on a periodic interval, then the spectrum is discrete. Okay, so you've got this picture here. And the projection valued spectral measure is just the notion of Fourier series. So given a G, you can compute its Fourier coefficients, GK hat. And then the spectral measure associated with the interval AB, evaluated at the point X, is just the partial Fourier series corresponding to squared frequencies between A and B. And then when you consider the scalar valued version, you just take the inner product with G, so it gives you back this energy formula. Now, when you go to an unbounded domain, for example, the whole real line, the spectrum becomes continuous. Okay, so this picture here, and you just replace Fourier series with the Fourier transform, and all these sums up here become integrals. Okay, so you've got these sort of generalized eigenfunctions. You can think of them these plane waves. The projection valued spectral measure is just a way of making that precise and in fact more general. But for us, all we care about is that there are spectral measures which are defined on this periodic domain corresponding to the frequency as we go around the circle. And it turns out that this will give us back the Koopman mode decomposition. So you can apply Lebesgue's decomposition theorem to split up this measure, the scalar measure, into a discrete part corresponding to Dirac's. These P lambda J are just the projections onto the associated eigenspaces. So each lambda J is an eigenvalue. And then you have a continuous part. So you have an absolutely continuous part with an L1 density. Okay, this is known as the Nikodym derivative. And then you have sort of the nasty leftover singular continuous part. Now, if, for example, we assume there isn't a singular continuous component, which, by the way, doesn't always hold, sometimes there is, then you can write G in terms of a sum of eigenfunctions corresponding to this discrete part and continuously parameterized eigenfunctions, where this this function here is related to the density up here. Okay, so at the end of the day, if all of that is a bit sort of abstract, The main thing to take away from the last 3 slides is that you get a rigorous derivation of this Koopman mode decomposition. And in effect, computing these spectral measures provides a diagonalization of your nonlinear dynamical system. So the goal is to compute these spectral measures because it will encode this information and also other information about the system. Okay, so what we're going to do is we're going to consider a Plumage type formula. So we're going to look at the Poisson kernel for the unit disk. Okay, so that's given by this function here, where epsilon is a smoothing parameter and theta is the angle. I'm going to look at a generalized Cauchy transform of these spectral measures. It's what you would consider a Cauchy transform, except I'm just parameterizing. Instead of 1 here, I've got e to the I theta as I go around the circle, and z is a point off the circle. Now you can rewrite the convolution of the spectral measure with this Poisson kernel in terms of a difference of 2 generalized Cauchy transforms. So this is like a Plumage type formula. So the way to think about this guy on the left here, or the top rather, is a smoothed measure. Okay, so you're smearing out the spectral measure with this smoothing kernel to get back a smooth function. And as epsilon goes to 0, this will converge to the measure in the sense of weak convergence. We'll look at rates in a second. But the key point computationally is that I can compute these differences of Cauchy transforms in terms of these inner products. Now I've done a trick here. I've used the fact that K is an isometry to mean that I only have to evaluate the resolvent or the shifted inverse outside the unit disk. Okay, so you'll notice that this Z, the shift, has modulus greater than 1. That's quite important. Okay, so you've got this difference of these inner products. Turns out that you can compute these robustly with error control using these 3 matrices. So in other words, you can compute smooth approximations of the spectral measure using the ResDMD discretizations. So we're going to do that for a discretization size nk. So here's a very quick example.
Sorry, quick question. So can the spectrum be something like a Cantor set? In this case?
The spectrum or the spectral measure?
The spectrum.
Yes, so the spectrum here is inside the unit disk, but you can have all sorts of yeah, exactly. You can have all sorts of weird behavior, and that's typically associated with the singular continuous part. So the algorithm that I'm going to talk about can deal with the singular continuous parts. It's just you won't get approximation rates. But yes, you can have all sorts of crazy behavior on the boundary. Yeah, essentially you can have any closed set along the boundary. Yep, good question. Okay, so let's just look at a quick example. This is an infinite unitary matrix and connected with orthogonal polynomials on the unit circle. But for the case of us, the case of the problem that I'm interested in, it corresponds to a sort of generalized shift on torus. So this is the dynamical system. I'm not going to go into that in much detail, other than the fact that I can have the I can write down the ResDMD matrices explicitly for this example, and I know what the spectral measure is. So this just gives me a good test example. So the spectral measure is very nice. It's absolutely continuous, and this is the density, this black curve here. I'm going to consider the approximation via those smoothed convolutions. So that'll be the curve in red. And these poles correspond to places where I evaluate the resolvents. Remember, the spectrum is this disk. So I'm going to do this for a fixed truncation size of 40 and decrease the smoothing parameter. So you can see we're okay for a bit, but when we get very close to the boundary, play it again, you become severely unstable. Now, the reason for this is that you're approximating the spectral measure associated with the truncation, which is just a series of Diracs along the boundary. Okay, so we want to avoid that. So a way to do that is to increase the truncation size adaptively as you decrease epsilon, or vice versa, as you increase the truncation size adaptively decrease epsilon. So let's look at that. So now as we approach the spectrum, we get a completely stable approximation of the true spectral measure. There is a caveat. The Poisson kernel yields slow convergence. So you can show that it's order 1 up to this logarithmic term as you decrease the smoothing parameter. Now, as you decrease the smoothing parameter, so what we saw on the previous slide was that we had to increase the truncation size. So let's look at that in a bit more detail. Here's the truncation size. Here's the error for different values of epsilon. And you can see that as we decrease epsilon, this curve becomes shallower and shallower. Okay, so we need a larger discretization size, which can be a problem in these data-driven computations, where it can be very expensive to actually get a hold of the matrix for a given truncation size. So we want to improve the rate of convergence on the left-hand side. There's a way of doing this very nicely using higher order variants of the Poisson kernel. Okay, so you can consider these sort of rational kernels. And there's a simple way of selecting the coefficients C, D, and the points, the point Zj, so that you achieve high order kernels and therefore high order convergence. And you can compute the convolution in exactly the same manner as before, but now you've got this sum of sort of this sum of M Plumage type formally. But again, you can compute these generalized Cauchy transforms using the ResDMD matrices. So we have theorems that give you order M convergence for the pointwise recovery of the spectral density, assuming it's sufficiently smooth. The LP recovery of the density, weak convergence, where you only need smoothness on the test function to get good approximation rates, and also recovery of the discrete part of the measure, which corresponds to the I shouldn't say discrete spectrum, the point spectrum of the operator. Okay, so these are the improved convergence rates for that particular unitary operator that we looked at. And also, if you care about the time it takes, you can do this so that it's effectively linear in the number of points where you want to evaluate the spectral measure. Okay, so here's a quick example for the double pendulum. So this is a chaotic system, okay, governed by this hideous system of ODEs. Okay, so for two angles, θ1, θ2, two momenta, P1, P2, given by these formulae. These are the spectral measures for different observables or different functions. So here I've got something corresponding to the first angle, the second angle, the first momentum, and the second. The blue curves are the Poisson approximation, which are over-smoothed. The M equals 6 curves are the sixth order kernel. You see you get a much sharper resolution of the spectral measure. So this was computed for epsilon equal to 0.1, I think. And so for a given epsilon, you can compute these convolutions with error control. So you can be certain that you're getting a highly accurate approximation of the convolution. Okay, so in the final part of the talk, I want to take it to the next level and consider high dimensional dynamical systems and learned dictionaries. So that's when D is potentially very, very large. Okay, so we run into the curse of dimensionality pretty quickly. So I'm going to consider in the final example of the talk a fluids example where I have a cascade of aerofoils. So it's periodic in this direction. And then I have some flow going over them. And I'll look at some data collected on a computational grid. It could be just as well be experimental data that I'm using. But you imagine that the pressure fields collected on all these sort of grid points. And then the dimension of your dynamical system becomes the number of grid or mesh points. So for example, if you considered a polynomial dictionary up to total degree 5, for a 5 by 5 grid, the dimension of the subspace that you're looking at would be about 50,000. Okay, so you can just about deal with that on your laptop. The example later on has D approximately 300,000. which yields an astronomical value of n. It's roughly 2 times 10 to the 25, which is much, much larger than the number of stars in the known universe. Okay, so all of this should hopefully be fairly familiar. The key point, of course, is that when d is above about 25, you can't use handcrafted dictionaries or functions to get your Galerkin approximation of the Koopman operator. So what we're going to do is we're going to use something called the kernel trick from machine learning. So there's a kernelized version of EDMD, which makes the cost linear in the dimension of the system, which effectively just computes a compression of the K EDMD matrix to a smaller subspace. So you implicitly learn a dictionary corresponding to the eigenfunctions of this compression matrix. Now, of course, the problem with any sort of learned method like this is that we have no rigorous guarantees that it will yield something suitable. So the question is, can we trust this type of method? Well, it turns out you can. You can use the fact that ResDMD converges with error control to effectively reverse engineer and evaluate how well your dictionary is, or rather how good a job it does at approximating the spectral properties of the Koopman operator K. So there's sort of two nice things about that. You get rigorous convergence theory as before, and a way of checking practically whether this sort of machine learning voodoo step works, right? So yes, we'll see that for 2 examples to end the talk. The first is in molecular dynamics. So here I'm considering a simulation, a Hamiltonian simulation of it will be a protein molecule. So this kind of thing has received a lot of attention. You might have seen AlphaFold, for example. But I'm going to collect data from this website here, where they just did a long time series simulation of this molecule. So here's the molecule. Here's the protein molecule. It's split into 3 parts. This core part in green, these 2 other parts which sort of move around and rotate around this core part. And there are 2 regions, these key parts, which have each of them have 2 dihedral angles, which give you the shape of the protein and therefore how it reacts with other substances in the cell, for example. So the dimension of the system will be roughly 20,000, which corresponds to the position and momenta of all of the atoms in this molecule. So here I'm computing the spectral measure associated with those 2 dihedral angles for the LID domain. Okay, so that's the angles here, and the NMP domain, the angles here. And I'm able to do it robustly, okay, rigorously compute these convolutions in the ambient dimension 20,000, and then you can do things like take some information about the system from these plots. For example, these have much more interesting frequency content at higher order frequencies. Okay, so I'm not a biologist, so I couldn't tell you exactly what this would mean for the molecule, but this is roughly what you'd expect for this system. The LID domain is more important than the NMP domain. Okay, so that's computing spectral measures in crazy large dimensions. Let's also look at computing spectra in large dimensions as well. So here we have a turbulent flow with Reynolds number roughly 4 times 10 to the 5. So this is that periodic cascade of aerofoils that I told you about. So I have an inlet and an outlet. The motivation for this example is noise reduction. So I'm going to look at the Koopman mode decomposition of the pressure field, which physically will give you back the sort of the noise that you actually hear as the flow goes over these wings. So the data will be collected from this paper down here. Okay, so each column corresponds to a different value of lambda in the spectrum with a different frequency corresponding to what you actually hear. DMD, the first row, is a version of EDMD where you use linear functions as the dictionary. Now, there are 2 problems with that. First of all, you don't capture all of the nonlinearities, as you might expect. And second of all, without applying this sort of residual framework, you don't get any sort of robustness guarantee. Now we look at residual DMD. where we use the learned dictionaries. And here we're able to capture the non-linearities of the system. Okay, so you get stronger vibrations here, turbulent fluctuations in the wake. But also, crucially, you can get a robustness guarantee by computing these residuals. Okay, so you get an error control bound. So for example, here you have an acoustic source, you might think, for the DMD, but it's suppressed by the nonlinear behavior of the system. And you can actually be fairly confident that this is the correct physical picture. Okay, so just to wrap up, I just want to point out this is part of a wider program on computation known as the Solvability Complexity Index. So a key question is, what is possible in infinite dimensional spectral computations? And what we've been doing is replacing sort of truncate and solve with a sort of flavor of or version of infinite dimensional numerical linear numerical analysis to solve these problems. Okay, and you can classify problems into a hierarchy that measures their intrinsic difficulty. So you can do this to show that algorithms are optimal and realize these boundaries. So there's been a lot of work on this recently, also in Cardiff as well. So some very nice papers on computing resonances and things like that. The framework can also be applied to barriers and foundations in AI. So we had a paper on that a couple of weeks back. Computing solutions of PDEs, for example, on unbounded domains, also optimization, precision analysis, computer-assisted proofs, and so on. So very quickly, I'm aware time is running out. I just want to give you two sort of adverts of this in different contexts. You can use these types of ideas to compute spectra with error control. So if you're given a self-adjoint infinite matrix, you can develop an algorithm that will converge to the spectrum and also give you a bound on the output. You can do the same thing with PDEs. You can also compute spectral measures of self-adjoint operators, which is perhaps the more familiar problem. So we have a software package on GitHub that does this for ODEs, PDEs, integral operators, and discrete operators. It all comes with rigorous convergence guarantees, and you can classify it in the SEI hierarchy. So there's these two papers here. And then finally, our recent paper on stability and accuracy in AI. So the problem of computing stable and accurate neural networks can also be put into this framework. Okay, so to conclude, I showed you some rigorous and practical algorithms that overcame the challenges of continuous spectra, lack of non-trivial finite-dimensional invariant subspaces, spectral pollution, and chaotic behavior. We computed spectra, pseudospectra, and residuals using this new matrix to give us ResDMD. We then computed spectral measures via convolutions with these rational kernels, and that gave us high-order convergence. And then we dealt with high-dimensional dynamical systems using ResDMD to verify learned dictionaries. That's it. Thanks for listening.
Thank you very much. Do we have questions for Matthew?
Can I ask a question?
Yeah.
If you could sit back to slide 10, there was something that slightly intrigued me there about this k-EDMD. The problem that the cure that you propose for a lack of spectral inclusion is to work with these pseudospectra.
Yeah.
So obviously, what's going on here, as I realised when you were saying this, is that the k-EDMD is ending up being a non-unitary approximation to k, and k, you were assuming at least has a unitary dilation.
Not in this part of the talk. So in this part, there's no assumption like that on k. But yes, exactly. Even if you were in that restricted case of having a unitary extension,
yes,
a part of the problem is exactly like you say, that the finite truncations aren't
so what I didn't understand was looking at the construction of the k-EDMD. What point in that construction is something like unitarity lost? Where does it?
Yeah. So it's this assumption. Sorry, it's this minimization problem here. Now there is a way of doing EDMD. So if you know that your Koopman operator is unitary, you can compute this. You can solve this minimization problem under the constraints that your matrix is. The matrix you end up with is unitary as well.
So you would want the constraint would be what is it B that has to be unitary?
Exactly. Yeah. In this case, yeah. Okay. Yes. So there is a way of doing that exactly, and there you would solve this. You would solve this issue. You'd still have to do this spectral pollution issue, but yeah.
Sure.
That would in some sense be easier.
That bit's well studied, yeah.
Yeah, exactly. Yeah. That's a very good point. So there are sort of there are now variants of DMD which look at sort of preserving structures like that. Yeah.
Mm-hmm. And so the KEDMD is the minimizing B in this.
Yes, exactly. Yeah.
Right. Okay.
Yeah.
Thanks.
Yeah.
Further questions? The audience. Yeah, Charles Bat.
Let me just switch the video on. You mentioned at the very beginning, I think, the case of continuous time systems. In that case, would you be thinking of approximating them by discrete subsystems, or would you adopt a more direct approach?
Yes. So you can, for example, if you have continuous time, then there's a version of the Koopman operator that effectively acts like a generator for the system, and you can apply similar sorts of techniques to try and approximate that generator. For example, if you take snapshots that are taken at sufficiently small time intervals, then as that time interval shrinks, then there are theorems that will tell you that you can recover the corresponding the operator. It's a little bit fiddly because you have to. There's always this sort of I guess trade-off between how small that time step could be and how much data you need to make it stable. But yeah, there is a way of doing that.
Yeah. Okay, thank you.
I'll ask a question, maybe naive. I'm just trying to think in my head about examples and how what you're saying would translate to these examples. So if I'm thinking about, let's say in the plane, I'm rotating the plane by pi, let's say. Now, if I happen to choose all my points here, x, if I happen to choose them on one ray out of the origin, I'm very unlucky, then the ray will just be flipped to the other side, right? How do I tell the difference between a rotation and reflection?
You'd need a better choice of initial points. There's essentially no way from that choice of data.
Okay, so okay, that's it would be hard.
But yeah, I guess sort of maybe the line of thought you're going down is, how do you, for example, show lower bounds, right, for these types of?
Yeah, okay. So if I'm in a two-dimensional space and I choose all my choice of points are along one ray, that's obviously not a good choice. But how do I know that I'm not encountering some other symmetry that I'm not thinking about, and then
So there is a sort of implicit assumption in all of this that this quadrature rule will converge. And if you think about it in terms of the solvability complexity index, that can add another limit to all of your algorithms.
I need to know something about the relationship, about the point between the points
exactly
and their images under the.
So you need some sort of assumption telling you. So if you wanted to overcome this extra limit, you'd need some assumption telling you how fast this convergence holds, right?
Okay. The X and the Y, right? So the X and the Y is post application.
Yeah. So there's nothing there's nothing really there in terms of choosing Y. Y in some sense is given to you via this formula, but it's all boils down to the choice of X and then also the regularity.
Right, but I can imagine that there would be complicated systems where if I choose my point somehow, let's say on some kind of rational lattice or something,
yeah,
my X
you
has some
trick
irrational component to it, then I can be very unlucky and not detect something about my dynamical system.
Yeah, totally, yeah, and sort of figuring out these are all sort of algorithms of when you can do it, but figuring out the lower bounds is still very open in this area.
Thanks.
I mean, I guess as a comment, I mean, tell me if you think this is correct, Matt. What Jonathan's talking about is perhaps even more of an issue for the high dimensional systems where you've got a set of data, and that data has come from somewhere, and you might, particularly in safety critical applications, you might want to, is this system always going to behave itself? Is it never going to blow up? And maybe all the data that that the experimentals collected come from initial conditions where everything was nice, and they just haven't revealed the one starting condition out of the many, the exponentially large number that you could have, the one starting condition for which something really nasty might happen. But I don't see what you can do about that.
No, I don't think
dimensionality.
I don't think there is any cure for that. Yeah, it's a very interesting question about sort of even if you assume, for example, these are collected randomly, and there could still be something nasty out there. And even if you had a rate in terms of m, the constant could be very, very astronomically large as well.
Yeah, I'm just sort of thinking, for instance, PDE is one thing that I was thinking about. All these new examples with the Euler equation where you have these solutions that are compactly supported in time. And so, if you wanted to think about, trying to do something like this for Euler, then it could be unlucky, and you're exactly choosing to look at a solution outside of its support in time, and then you're just saying 0.
I don't think there's any way around it. I think whatever, even if you don't go by Koopman or anything else, exactly, because you've got two dynamical systems that produce the same data on those data points. There's no way of telling the difference.
All right, so I suppose this is a good time to thank Matthew again and postpone further questions to the informal chat. So thank you very much.